So we'll start the presentations. Our first presenter is Dr. Fardis Nakhaei he's an assistant research professor in the mining and explosives engineering in Missouri Santee, and he is going to talk about critical elements recovery from sulfide tailing with emphasis on tellurium.
Thank you, Prof. Thank you, Prof. Good morning, everyone. My name is Fardis Nakhaei. I'm delighted to present our research on critical elements recovery from sulfide tailings. As you know, sulfide tailings are the main host of critical elements such as gallium, germanium, bismuth, tellurium, and antimony. We recently published a comprehensive review paper in separation and purification technology, and we addressed all these elements in this paper. In this presentation, I will focus on recovery of tellurium from sulfide tailings. Here is an overview of what we'll be discussing in this presentation. First, current state of the global tellurium market and strategies to improve tellurium supply chain. I will touch upon potential of copper sulfide tailings as resources for tellurium recovery. Then I introduce the tailing samples, their characterization. And finally, I will present the flotation experiments and experimental findings and concentrate characterization. Tellurium with a concentration as low as 1 to 5 ppb in the Earth's crust is even more scarce than gold and silver. Unlike a standalone tellurium deposit found only in China, tellurium is typically found associated with pyrite and chalcopyrite and any sulfide minerals. But it's mainly recovered from copper anode slimes as a byproduct in copper processing, during copper processing. Despite its scarcity, tellurium plays a crucial role in various applications, particularly in photovoltaic cells and thermoelectric devices. Given the increasing demand of cadmium telluride solar cells, its limited reserves, relatively low recovery, its lack of substitute, and the limitation of old scrap for recovery, tellurium has been classified as a critical element in the US. In this slide, you can see the overview of the global tellurium market. China is the largest producer of tellurium, accounting for 340 tons per year, equal to 55% of total tellurium production. And 90% of this tellurium comes from copper anode slime, and only 10% is derived from one tellurium deposit in China and recycling. 40% of tellurium is used in solar cell panels, 30% in thermoelectric devices, and the remaining is applied in metallurgy and chemical industries. Based on the development outlook of cadmium telluride supply chain in the US, the cadmium telluride photovoltaic industries hold a significant growth with a potential to triple by 2030. Therefore, a six-fold increase in tellurium production is needed to support the annual production of photovoltaic panels. However, this achievement faces several challenges. First, the limitation of global supply of tellurium by China creates supply chain vulnerabilities. Second, the US faces risk in its tellurium supply chain due to high dependence on imports, along with low recovery from copper anode slime. The question is, how can we effectively cope with these difficulties? One proposed solution is increasing tellurium production by supply chain diversification. It involves exploring unconventional resources and developing tellurium enrichment from these resources. Let's investigate the global tellurium supply chain within the copper processing plant to identify the best way to increase tellurium capacity. Ore extracted from mine is transferred to the copper process to mineral processing plant to produce copper. Copper is then smelted to convert to copper matte. The copper matte is then purified in converting furnace, anode casting, and electrorefining process to produce copper cathode. In this flow sheet, it's estimated 40,000 tons of tellurium are extracted from copper mine. However, only 10% of this tellurium are transferred to the concentrate. The remaining 90%, equal to 35,000 tellurium, are transferred to tailings. Considering the significant amount of tailings generated in copper processing plant, it's essential to investigate the characterization and separation techniques for extracting tellurium from flotation tailings. In this study, the samples were obtained from old copper tailing dam in North America, and they were taken in various locations and depths via core drilling. After homogenization and preparation of the samples, particle size analysis were done using sieve shaker and laser diffraction analysis. Major and mineral phases were identified by XRD scanning, SEM, and test scan integrated mineral analyzer. And the chemical composition were determined by ICP-MS analysis. Mineralogical analysis showed that the pyrite is the main host of critical tellurium and critical elements. Therefore, we conducted flotation experiments based on the recovery of pyrite. Finally, mineralogical analysis were done to identify tellurium-bearing minerals, their abundance, and their liberation in the concentrate. The particle size analysis showed that 80% and 50% of the head sample are finer than 180 and 85 micron, and nearly 25% of the head sample is smaller than 25 micron. ICP-MS analysis showed that the head sample contained 0.14 and 3% copper and 3% iron. Tellurium, silver, and gold concentrations were relatively low in the head sample, measuring 0.4, 0.7 ppm, and 150 ppb, respectively. There were noticeable variations in the chemical composition of the head sample in different size fraction. Copper concentration were high in both coarse and fine particles, showing that these particles were transferred to the flotation tailings because of the poor liberation of coarse particles and low floatability of very fine particles. And the concentration of tellurium and silver increased as particle size decreased, ranging 0.8 ppm and 1.14 ppm, respectively, for particles smaller than 15 micron. This slide shows the distribution elements in different size fraction. Approximately 35% of silver and tellurium was found in particle size smaller than 15 micron. And nearly 55% of these particles were present in particles between 180 and 15 micron. And 35% of gold was found in coarse particles bigger than 125 micron. This graph helps us to better understand the recovery of these elements. For example, if we discard very small particles, less than 50 micron, and very big particles, 180 micron, from which these particles have negative effect on flotation. In total, 45% of these elements would be lost. Based on TMI analysis, 95% of the head samples contain silicate, and total contribution of sulfide-bearing minerals was 2.4%, shared by 2.2% pyrite, and chalcopyrite was the primary copper-bearing minerals, accounting for 48%. Tetradimite was the most common tellurium-bearing minerals, equal to 75%, while hesite contributed a minor amount of tellurium in the head sample. Gold was found as electrum, and complex phases including silver, tellurium, and selenium. And all these minerals were fine-grained, less than 7 micron, attached to pyrite or as inclusion in pyrite. These backscattered images shows tetradimite and hesite inclusions locked in pyrite, and also an electrum and a complex of gold, silver, selenium, and tellurium attached to pyrite. We conducted flotation experiments with the head sample and different size fractions. Flotation with head samples led to a significant increase of concentration of these elements. For example, tellurium concentration rose from 0.4 ppm to 4.5 ppm, and silver increased from 0.7 to 6 ppm. And iron jumped from 3% to 16%. Looking more closely in the tellurium bar chart, we can observe the highest concentration of tellurium belong to intermediate size fraction, ranging from 180 to 38 micron. We conducted a flotation experiment with the optimum size. The results were promising, showing that the concentration of tellurium reached 7.4 ppm. The highest tellurium recoveries were obtained from the intermediate size, ranging from 180 to 38 micron, ranging from 50% to 97%, and a significant amount of tellurium was lost in coarse and fine particles. Tellurium, silver, and gold recoveries reached 65%, 40%, and 30% in the flotation with the optimum size. Since a significant amount of tellurium and precious metals are in coarse and fine particles, discarding these particles is not our final goal. We are exploring several methods to recover these particles. Based on the mineralogical analysis of concentrate, 61% of concentrate contained pyrite. Other mineral sulfides were chalcopyrite, molybdenite, and cobaltite. Tetradimite was the most abundant tellurium-bearing minerals in the concentrate at 0.15%. This value is the same as the concentration of chalcopyrite in the head sample. It's a great value. Other trace tellurium minerals were calaverite, altite, and native tellurium. And tetradimite accounted for 96% of the total tellurium and occurred as inclusions in pyrite. Gold phases consisted of native gold, electrum, and several complexes. In the following slides, I'm going to show you very interesting backscattered images of concentrate. In this slide, you can see tetradimite inclusions attached to pyrite, and tetradimite grains associated with chalcopyrite inclusion in pyrite, and almost big, large tetradimite grain and fine galena inside the pyrite. We found large and fine tetradimite inclusions in pyrite. In this slide, you can see the complex inclusion of gold, silver, tellurium, and selenium in chalcopyrite and bornite, a complex inclusion of calaverite with copper, nickel, and cobalt. And you can see the calaverite and tetradimite minerals in pyrite. We found chalcopyrite containing inclusion of a palladium telluride, pyrite with inclusion of nickel telluride, melanite, and calaverite, and very interesting backscattered image, large and fine tetradimite inclusions and fine inclusion of gold, silver telluride associated with native telluride. You can also see the calaverite inclusion in pyrite, very interesting three-phasic inclusion of calaverite, bismuth telluride, and native telluride in pyrite, and several tellurium minerals like calaverite and bismuth lead telluride in the other backscattered images. You can see native gold inclusion in chalcopyrite, electrum inclusion in potassium feldspar, and electrum attached to pyrite. Last but not least, native gold inclusions in liberated pyrite and log pyrite were found. As an inclusion, pyrite is not a gang mineral. It's a nice host with precious guests. Thank you so much.